In this video, we're going to take a look at Rolle's theorem and the mean value theorem. So let's begin with Rolle's theorem. So let f be a function that satisfies the following three hypotheses. First, f is continuous on the closed interval AB. So notice that this interval has to be closed. Number two, f is differentiable on the open interval A to B. And then number three, f of A equals f of B. This means that when I plug in the values for A and B, they are the same y value. So if we have all three of these conditions satisfied, then there's going to be a number C, which is between A and B, such that f prime of C is equal to 0. So meaning that if I find the derivative at C, then that derivative is 0. So here are some graphs to depict these three conditions. So the first one is that we have A at this endpoint here, and B is at the other endpoint. It's continuous, so it's differentiable here because it's also a flat line. Then we know that there is a point, C, that will give me a derivative of 0. And you can see that it's flat right here. And for this case, there's actually a lot of them. So we can have C1 and C2, and notice that there's another spot here where the derivative is also equal to 0. In the second graph, we have A and B, and we can see that there's a point here, C, such that the derivative is 0, and that gives us a horizontal tangent line. In the third graph, we have A and B, and this one gives us two of them. So we have C1 here, and then there's another point here, C2, which also gives us a horizontal line. And sometimes we can have even more. So we have C1, there's another point here, C2, and also over here, C3. So all of these three spots will give us a horizontal tangent. So in each case, it appears there's at least one point, which we'll call CF of C on the graph, where the tangent is horizontal, and so we have that the first derivative is equal to 0. All right, so let's actually take a look at an example. So I want to verify that f of x equals negative x squared plus 4 from negative 2 to 2 satisfies the conditions of Rolle's theorem. And we're going to find the value of c, which makes it true. So we know that f of x is continuous on the interval negative 2 to 2, and it's differentiable, which is our second condition, on negative 2 to 2. So notice this is a closed interval. This is the second one I have written is an open interval. And it satisfies because f of x is a polynomial. And we know that all polynomials are continuous and therefore differentiable. Now the third condition, what we need to do is check that f of negative 2 and check the value of f of 2. So when we plug in negative 2, we get negative 2 squared plus 4. That gives us 0. Plug in 2, and we also get 0. So therefore, Rolle's theorem applies. All right, so we're going to go ahead and find out what c value. So we have the first derivative is equal to negative 2x. And so we want to find out what that c value is. So f prime of c equals negative 2 times c. We're going to set it equal to 0 because Rolle's theorem says that the value will be 0. The derivative will be 0. And we see that c is equal to 0. So since c, which is 0, is in the interval negative 2 to 2, this value works, or it satisfies. So now we're going to go on to the mean value theorem. So to start this, we need to start with a secant line. And a secant line is a line that's drawn through 2 points on a curve. And the mean value theorem relates the slope of the secant line to the slope of a tangent line, or the average rate of change to the instantaneous rate of change. So the secant line would be the average rate, tangent line would be the instantaneous. So the mean value theorem is actually a little bit more general than the Rolle's theorem. It only has 2 conditions. So the first condition is that f is continuous on the closed interval, again, from a to b, and f is differentiable on the open interval this time from a to b. So when this happens, there's going to be a number c that is from a to b, such that the first derivative is f of b minus f of a divided by b minus a. So it's saying that the first derivative is equal to the slope. Or, in other words, we can also say that f of b minus f of a equals f prime of c times b minus a. All right, so the picture below shows why this makes sense. So we have a secant line, which I've drawn from a to b, and the mean value theorem says that somewhere in between a and b, there's going to be a point c in the middle here, where the tangent line is the same slope as the secant line. So lines with the same slope are parallel. Now to find a point where the tangent line is parallel to the secant line, you can think of it as just kind of sliding it. So for example, let's say that we started with this line here, and then we're going to keep sliding this without changing the slope, and we're going to keep moving it up until we find out where that point is. And we see that this is where it just hits the graph right here at point C. Now, this can only work if the curve is continuous and differentiable. Now, the following curves here, they don't have a tangent line parallel to the secant line. And I'm going to show you a couple of examples. So, for example, we can have this curve here. And let's say that we have this point A here. And then there's an open point B here. So because it's open at point B, then f is discontinuous at B, and that's why it doesn't satisfy the hypothesis, and therefore the mean value, we can't use the mean value theorem. So I'm going to say that f is discontinuous at B. So therefore we can't find a tangent line parallel to secant line because there is no secant line. Another example where it doesn't work is if we have something that looks like this. So this is A, this is B. Now there is a point C in between, but f is not differentiable because we have this corner here at the point C. So f is not differentiable at C. Now, there may be more than one value for C which works. Similar to what we saw in the Rolle's theorem. In the graph we saw sometimes we had 1, 2, or even 3 or even more points where the slope was 0. The same thing can apply to the mean value theorem, where we can have several points on the graph where the tangent line is parallel to the secant line. So in general, finding a value of C that works may be difficult. The theorem only guarantees that such a C exists. So let's take a look at an example. So state whether or not the function satisfies the hypotheses of the mean value theorem on the given interval, and if it does, we're going to find the value of C on the interval that satisfies the conclusion of the theorem. So we see here that x cubed plus 3x squared, it's a polynomial. So because it's a polynomial, then it's going to be continuous and also differentiable. So we're going to write that down. So f of x is continuous on the closed interval -5 to 1 and differentiable on the open interval -5 to 1 because f of x is a polynomial. All right, so we're going to find the first derivative. So f prime of x is equal to 3x squared plus 6x. We're going to set this with c instead of x. Can't seem to erase that. Okay. All right, so I'm going to now say that 3c squared plus 6c is equal to, and what I'm going to do is I'm going to put -5 and 1 into my function because that's how I find the slope. So 1 is my second value, so I'm going to say that 1 cubed plus 3 times 1 squared minus 5 cubed plus 3 times 5 squared, all divided by 1 minus -5. That should equal 3c squared plus 6c. So that's the number I'm trying to find. I'm trying to find out what c is. So I have 3c squared plus 6c. And then on this side, I have 1 cubed plus 3, so it's 4. And then I have 125 plus 75. Oh, sorry, negative. Oh, and I forgot to put the negative here. So put the negative in. So negative 125, and then plus 75, I'm going to have plus 50. And that's all divided by 6. So 3c squared plus 6. C equals 9. Move everything to one side. Set it equal to 0. And I can factor 3 out, so let's do that. And then I can see that this is factorable. So I get c plus 3 times c minus 1 equals to 0. So c equals -3 and 1. Now, c equals 1 is not on the interval, on the open interval, okay? So c equals 1 is not in the open interval. -5 to 1. It's actually an endpoint. So therefore, c is only equal to -3. And then you can try the next one on your own.